All right, everyone. Welcome back to this channel. Welcome back. Welcome to this video. So, in this video is all about. In this video, we are going to learn about direct preference optimization (DPO). It's a technique that has been introduced in this paper by Stanford University. I think some people at Stanford University have published this paper. So, we are going to go into this paper, what it really solves, what it achieves, and um, it is even like you know a lot of people have also been like talking about it, and it also has been like used in many projects in like fine-tuning many models, many LLMs. This technique has been used, so we'll basically look at this technique and what this technique is, right? So we'll just look at it in a high level. We'll just look at this technique, right? So again, feel free to read the abstract or something in the important parts. I'm going to go directly into what this solves. So before learning about DPO, before learning what it solves, what it achieves, you have to learn. You have to know about RLHF, reinforcement learning from human feedback. I think I have already made a video on it. I have already made a video on RLHF, reinforcement learning for human feedback. Now I'll just quickly go through it. What it does, what RLHF does, right? Um, so basically, when you are building an LLM, after build an LLM, let's say, right, you build a LLM. Just think this is an LLM, the model, right? So after you build an LLM, right? Uh, you have in order to solve some problems, right? Sometimes the LLM may uh, show undesired behaviors, right? Undesired behaviors, like maybe LLM turns violent, right? Maybe sometimes LLM turns violent, or maybe sometimes it answers questions that it should not answer, right? For example, if a customer asked, or if a user asked, how to build a bomb, or how to manufacture something, right? Something that is not good, right? We want the LLM to answer in the relevant manner, in a nice manner, in a desired behavior manner. How do we do that? So basically, this is called aligning the LLM. What this is called is aligning the LLM to desired behavior, right? Right? We want to align the LLM to the desired behavior, or in other words, we want to instill the LLM with uh, our preferred behavior, right? That is what we want. That is the goal. So in order to have this, in order to perform this, in order to align the LLM, RLHF is generally used. It has been used for as a conventional method. So in RLHF, what we'll be doing is we will train a reward model, right? I'm sorry. We'll train reward model. So this reward model basically captures or understands the preferred behavior, right? So what we'll do is we'll have a data set, right? We'll have a data set. This data set consists of many questions and answers, right? For example, for question X, there may be two answers, y1 and y2, y1 and y2, and given this question and these two answers, we'll have the desired answer. For example, y1 is a desired answer, while y2 is not the desired answer. So we'll have a data set like this. So we'll have many x's, many x's, many rows, uh, many questions and many answers, and each question will have two answers or more answers, two or more answers, in which the desired answer is shown. So this reward model is trained on this data set. And the goal of the reward model is to find the best answer, right? The reward model will learn which answer is better, right? That is what it learns. So we'll have a binary or multiple classification model, multi-class classification model, in which given the question and a set of answers, it picks the right answer, or given a question and an answer, it rates the answer, right? It rates how much desired behavior that answer has, right? So for example, you have a reward model that takes an x and y, sorry, that takes an x and y, This model predicts, what it predicts is uh, how preferred y answer is given x. So given question x, how preferred is answer y? How good is it? After training it on data sets, there are many data sets again. After training the reward model on this data set, we will perform RLHF. RLHF, RLHF, sorry, not RLHF. Okay, RLHF. So we'll perform reinforcement learning, RL, reinforcement learning. And this reinforcement learning is actually quite simple. Reinforcement learning, in reinforcement learning, you'll have an agent, you'll have an environment, and in this agent tries to interact with this environment, and the goal of this agent is to gain the maximum amount of reward, right? The greater the reward it gains, the better it does. So basically, it learns to gain better reward, and we will uh, place this LLM. We will place this LLM uh, inside an environment. Well, not necessarily an environment, but this LLM will try to gain more reward from this reward function that we have previously trained, right? We have already previously trained this reward function. This LLM will try to gain more reward from this reward function. That is its goal, right? So that is its goal. And the model, so in order to gain more reward, the model will update its weights, right? The model internal parameters will be updated in order to gain more reward. That is the, and this is all. This is the overall process of RLHF, right? So we could look at this in the paper also. I think they also shared in the paper. Go here, predetermined. Yeah. So this is the reward modeling phase, in which this is the loss function for the reward model, right? While training the reward model, this is going to be the loss function for the reward model. Reward model again, reward model is trained on data set in order to capture, right? The reward model will predict a reward on how relevant or how preferred a given answer is given a question, right? And so this is the reward loss function. So given the reward, the actual value, given the data set, the question and the answers and their corresponding rewards on how preferred the answer is. So given that data set, we will run this algorithm in which, right? So here YW is the preferred answer and YL is the non-preferred answer, or YL is the bad answer and YW is a good answer. And we'll have this loss function in which we want the model to predict higher reward for YW and lesser reward for YL. Again, this is a negative likelihood loss, in which, so therefore the model will try to increase this. So generally the model tries to decrease the loss function, and since we have a negative sign, this term should be increased as much as possible. And in order for this term to increase, the model should give higher reward to YW, the preferred answer, and lesser reward to the unpreferred answer, or neglected, or what we call it, rejected answer, right? That is the goal of that is the loss function of the reward function, reward model. That is loss function. That is that, the model tries to decrease this metric value, right? And after that, after having the reward function, again we have this formula in which the model's goal is to maximize this. The model's goal is to maximize the reward, right? R pi, right? The model tries to maximize this reward, and also we have another term which is minus beta times KL divergence of this. So basically, KL divergence shows us how different one value is to another, right? Here we are doing the KL divergence on pi theta and pi ref. So here pi ref is the previous model, the original model, and then pi theta. So pi ref is the pre-trained model before fine tuning, before doing the RLHF phase, and pi theta is the current model after changes, after updating the weights, and we'll basically make sure that the pi theta, the current model, is similar to the previous model. We'll make sure that the current model is equal, or it tries to remain equal to the previous model. This is to make sure that there is stability in training. It is one of the most important factors in RLHF, in fine tuning, of course, just to make sure that the model does not, just to make sure the model learns slowly, the model takes slow steps, and it really understands everything, not just like go big and get lucky sometimes. We don't want that. And that is why we have this scaled level system. And this term beta controls how, this is hyperparameter. We could choose it while we are training. We could change it while we want if we're training. So this term beta, it controls how much importance we should give for this term. How much importance that we should give for stability. If we increase beta, then it means that we want the model to be more stable. If we decrease beta, we want the model to be, we could accommodate less stability also. That is what we means. Again, this is a hyperparameter which you can choose. Right. So that is RLHF. That is what we'll be doing in RLHF. And we could see here. Right. So due to discrete nature of language generation, this objective is not differentiable and is typically optimized with reinforcement learning. Right? Yeah. So this is again optimized with reinforcement learning. And the goal of the model again is to use reinforcement learning to increase the reward. So basically increase this function, right? Increase the reward minus beta of, well, all of this. So this is RLHF and it has some problems. Number one, it is more, well, it is pretty lengthy. I should say we should train a reward model separately and then do all this process again, do reinforcement learning. And also the parameters might be very large. So much computation power is required. And also sometimes this model RLHF RLHF method might not be very stable. And that is where DPO comes in, direct preference optimization. They have the, in DPO, we'll remove all the process of training reward model and all that, and we'll replace that by a simple loss function, which we could minimize in the fine tuning phase, right? In order to instill the desired behavior. So all the derivation is done. When, yeah, definitely, if you want, you could just definitely do take a look at it. But I think the final result, right? I think the final loss function itself is, I think, pretty intuitive. We could really understand it if we really think about it. We don't have to do all the algebra, right? I mean, it is quite intuitive, I think. So this is a loss function, right? This is the loss function of DPO, right? Pi theta again is the current model. Pi ref is the original model, right? Original pre-trained model. Here we don't even have to like use the reinforcement learning in DPO. It is like pretty direct, right? So here we have log sigma. Sigma is nothing but, it converts a value in the range of 0 and 1. That is what it does. And then again we have beta. It's all again a hyperparameter. I think it also, I think, plays a pretty huge role, beta. Anyway, so we have a log function, log of pi theta probability, the probability of the current model, the probability of YW given X. Right. So we'll get a probability of the current model. So again, the model has to decrease this, right? So the goal of the model, we'll train the LLM, we'll fine tune the LLM with this loss, and the goal of the model again is to decrease this loss. And in order, again, this is a negative loss, so therefore, in order to decrease this whole value, we need to increase this term. We have to increase this term log of all this. So in order to increase this should be increased. This term beta log of pi theta of YW given X by pi ref of YW given X. We want to increase this term. And how do we increase that? Right? We could that is what we're doing. Right? We're having the probability of YW. YW is a preferred answer. The answer that is preferable. So in the data set, we are going to have the preferred answer and the rejected answer, right? So we are going to get the probability of y theta, so probability of the preferred answer by our model, and we're going to divide that by pi ref of YW. Pi ref corresponds to the original model. Again, we are making sure the model doesn't diverge too much, right? We are making sure the model doesn't diverge too much. And then we're going to subtract that by beta log of y theta of YL. YL corresponds to the answer that is rejected given x, and then we will divide that by pi ref, the older model, how much probability it gives for yl, the rejected answer given x. So here it is actually quite direct, right? We'll directly prompt the model. We'll directly ask the model, like we'll just go and we'll just ask the model to increase the probability for YW, right? And this decrease the probability of YL. And also we directly ask the model to not make huge amount of changes, right? All this, right? We'll directly just have this loss function. So in order for the model to uh, decrease the loss function, the model has to give higher priority for or higher probability for the preferred answer. Right? The model should give higher probability for the preferred answer and give lesser probability for the rejected answer, while also maintaining stability. That is not making huge amount of changes, right? Making small amount of changes. So that is also, so that is a loss function, right? So in order for the model to gain smaller loss, which is the overall objective of the model, that we're going to perform gradient descent, we're going to calculate the gradients, and then we're going to do back propagation, all that, right? So in order for the model to gain lower loss, the model has to do this. The model has to give higher priority for YW and lower priority for YL while maintaining stability. Right, these are the gradients. We could see, yeah, I think r hat is this term pi theta of y given x, and then we have all this. We have to, we will get the same thing again. So we should increase likelihood of the YW and decrease the likelihood of YL, which is actually quite straightforward. I think very much straightforward, in fact. And as strange as it sounds, you may think that it doesn't work. Right? You may think that is just like pretty stupid, right? Rather than having separate processes, right? Just like RLHF, you might think it might not work. It might not be compatible this method, but they have also theoretically proved that this method is more stable, right? I think I know they have also given like this theoretical analysis of DPO. I should probably like read it. Okay, so yeah, I'll probably make another video on this, the theoretical analysis separately. But I think they have found that that DPO is more stable. That it also has a normalizing term, making it learn slowly. I think that is what they have showed here. Right? There is like the normalizing phase, non-normalizing thing also, because like we are dividing, right? Maybe that is also one thing. Yeah. So anyway, and they also put like the PPO algorithm, which is the algorithm that I showed you earlier. The reinforcement learning algorithm. They have showed that it is kind of unstable, which also proves that DPO is better. And the main thing that I want to get here is the experiments part. So they have they proclaim that they have done some experiments on like 3 setups. They had 3 tasks essentially. One is control sentiment generation, predicting the sentiment of a text or something. And then they have summarization in the second task, summarizing content. And then third, they have question answering, single turn dialogue, predicting the next word. So they've had these setups, right? They have maintained these setups, and they have evaluated. So for the sentiment classification, I think they have used a simple model. I think a simple sentiment classification model to evaluate the performance. And then for summarization, they've used, I think, GPT-4. And then for I think for let's see, um, yeah, again, I think they have used GPT-4 for question answering also. Okay, anyway, so they have performed these experimental setups, and they have found that, yeah, DPO's reward slash scale trade-off. Right? Trade-off refers to balance. So DPO, they have found through their experiments that DPO gets better reward, and at the same time maintains a good KL evidence score together compared to PPO, which is actually quite nice, right? Which they have found through their experiments, and they also found that let's see what you have here. If you want DPO to be much more robust to sampling temperature than PPO, the performance of it degrade. Okay, anyway. So, I think it also works at high temperatures. I think temperatures refers to randomness, you know, instilling more like creativity. I think maybe that is what temperature means. Um, and then, and also like on one single turn dialog also, I think DPO is the only computationally efficient method that improves over the preferred computations in the Anthropic HS dataset and provides similar or better performance on computationally demanding best of HS dataset. It also, I think, is quite better. I think that's it, right? That shows us that DPO is maybe better than RLHF because moreover it is also computationally efficient. It is actually quite straightforward, right? Will directly increase the probabilities likelihood of the preferred answer and decrease the likelihood of the dispreferred answer or the rejected answers. Um, they also have some derivations and also some uh, text. Maybe please check it out if you are interested. I've actually like fine-tuned Llama 2 on this. I've actually managed to like fine-tune Llama 2 using DPO. No, I just did it like yesterday. You know, uh, it's quite simple. You can actually use DPO now. I think it is built-in. It is built-in. In fact, you could use it. So I'll just show you how to use it. So I think from TRL I think is from Hugging Face. So you could import DPO trainer. It is already pre built for us, so we don't have to like take care of all the details. And then we could call the DPO trainer. We could have the model and model ref. So when model and model ref is like the same model in the start. In the model and model ref are essentially the same model. I just called it like 2 times, as you can see here. And then we'll have a parameter beta. Again, please experiment if you're interested. We'll provide the dataset. In here, I have used like the stack exchange dataset. I'll show it to you very quickly. Stack exchange paired dataset in which they have question, right? The dataset is actually quite simple, quite nice. And also, so they have a question and like two responses, response J and response K. I think response J is preferred. I actually wrote the code above here. Let's see data. Yeah, so the chosen is response J. So response J is the preferred response and response K is the rejected response, right? So we have this data set. They're actually quite big. It might take some time to load. And again, I've faced the problems while training also, like some what GPU problems. I don't know why that came. I may need to like buy the subscription or something, Collab subscription. But anyway, it will work. So you can use the GPU uh, trainer library that is also already pre-built. And then again, you could feel free to like play around with the parameters. I have used like Llama 2 7 billion parameters, and then so that's it, right? Thank you for watching. I hope this video was useful, and I'll see you in the next one.